I want to talk about homework problem 2 because homework problem 2 is not precise. It doesn't give you enough information to get it right without guessing. So I want to give you the additional information to get it right and not guess. So problem number 2 says that you start with a coil of wire that has, I don't remember if it's the same for everyone, but the one that I did last night had 8 turns. What is the symbol we use for the number of turns? N, okay. My brain clearly is working. And it's made out of electric cable. It's sitting on the floor in your garage, and it has a certain radius, it tells you. And then you go from there. It says that the magnetic field of the Earth is 20 degrees from the plane of the garage floor, or from the garage. No, it says 20 degrees from the garage floor, I think, something like that, which isn't super clear. So the first thing you have to have clear is when they tell you that. Let me draw X, Y, and Z well, X, Y, Z, okay? Or if you prefer, well, we can give it north, south, east, west, up, down. This is going to be north and east and up for the directions. Okay, so having that, the electric field or the magnetic field of the Earth is going to be 20 degrees from the horizontal. So in our picture here, I'm going to put it under the y-axis at an angle of 20 degrees below the y-axis. So now that we have that, we can calculate the flux, because what's the equation for flux? Magnetic flux in this case. Okay, BA, cosine of the angle between the normal and the magnetic field. So in this case, what direction is the normal to my coil? Okay, up. So my area is like this. And now we can have some sign differences depending which way you do things. Just use the positive outcome here. So if my area is up, I think when I sent you the email I did, is down or something like that. Yeah. Then it's going to be 90 plus 20 is 110 degrees between the area and the magnetic field. And so I have theta initial, I said 120, it's 110, is 110 degrees. And then we rotate it by 90 degrees. But there's the second thing that even with parsing the words very carefully, you can't get. What direction do they rotate? We know the magnetic field is going to be north and downward. What if they rotate it from this angle here to this angle here? What's the angle between the area and the magnetic field if they rotate it like that? 0. It's going to be 90 degrees is the angle between the area here and that. But if they rotate it like this, then it's going to go to 20 degrees. Right? So it depends on which way they rotate it, what your ending condition is. And so the answer is it's going to be rotated so that in the second case, it's like this. So the area is going, I'm going to do it as going back. It's just consistent with the way I was thinking about it. And so you still have the magnetic field like this. And so what's the angle between the two now? Okay, can you say that louder?
It's the same, it's parallel to the ground, so it's still the same angle as it is to the ground.
Okay, Since I said to just use the sign to give you positive, I'm just putting in the 20 degrees like she said, right? If you want to be more precise, you'd say, well, going this direction, it's 160. Going this direction, it's 200. But if I just use cosine 20, it'll give me the positive. I said to use the positives in both cases. So with that information, now you can solve it. So I wanted to make sure I gave you that information. One more thing that can be tricky. For part A, it asks you about the change in flux through a single loop. So even though there's 8 loops, I'm just going to take the BA for the flux, not NBA. For part B, it asks you for the induced EMF. Well, then you have to put the N times the change in flux over change in time. And once again, just put a positive value for the average voltage.
I was just going to ask about that. Why is it a positive value for that?
We don't have information to tell us about direction.
Okay.
So it depends on which way you're measuring, if it's going to be positive or negative.
Okay.
Right. And remember when I talked about Lenz's law, which is the next slide. The next 2 slides are clicker questions. So you're ready. Lenz's law, its purpose, the minus sign is to point us to Lenz's law, which tells us the direction. So I generally ignore the minus sign, except for reminding me I need to go to Lenz's law to know which direction is positive. And you understood number 1, right? After I wrote to you.
I had to use someone else to help me.
Okay, let us go to clicker question numero 1. What will not produce a magnetic field? I meant to say something else. And induced voltage is what I meant to say. I made a mistake. Right, we were studying Faraday's law of induction about inducing voltages. Only one person hasn't answered a question yet, so there was no question about whose card this is. Keela. You're the only one who hasn't answered so far. Well, wait. We still... Nope. Oh, yes. Caitlin hasn't answered. Okay, yeah, you just did. Or maybe I misread, but you're answered now. Okay, so let me give you the answers before. 6, 10, and 3. So we had the barest majority said moving a wire through a constant magnetic field. So, Gila, which one did you answer and why?
I answered B.
Okay. Why?
Honestly, can't tell you why. Because I just think but I figured since it's a constant magnetic field, it will reduce it.
Okay. Now, there are 2 here that have constant magnetic field, right? And if we look at these, the first one, changing the magnetic flux through a stationary coil. Is that going to do anything in the coil? Faraday's law of induction says so if we change the magnetic flux, that is the theta B is changing with time, is that going to produce something here? Yeah, it's going to have to. So this one here, this one definitely will produce, so it's not the answer. Then we have the other ones that are moving through a constant magnetic field. If I move through a constant magnetic field, and yeah, I think I should have read this question more carefully this morning when I was editing slides. If you're moving through a constant magnetic field and you're not rotating, what's happening to your flux? Stays the same. Now, in the one where it's just a wire, the wire doesn't have a loop. There's no way without a loop that it can make a magnetic field. There's no way it can have a current. Because the 2 really were the same idea. You produce a magnetic field if you have a current going through something. So in the wire, the instant it starts to move, you would have a sudden current to build a voltage difference because of the forces on the charges, and then it would not change. The coil moving through a constant magnetic field, if it's translating like this, it's also not going to do anything. Since I wasn't clear in my words, I do have an out for my bad question. Rotation is a motion too. If it's rotating or something, then the flux would change and it would work. So really, this was a poorly worded question. I did this, then I went to bed, then I remembered I had an email with the question from Aaron. I got out of bed and answered the questions. Probably should have just, gone to bed earlier. Okay, let's go to the next question. Whoops. There we go. Went through 2 questions at once. What is Lenz's law? Well, so everyone knows, she sent the email at 4. It's not like it was a late email. I got it just as we were starting our UAV class. And so, I can't do anything there. I forgot. What is Lenz's law? Okay, everybody's answered. Really? It says 19 people responded. It's only showing me 4 out of 5. Okay. It shows 5 here, and then it shows 0, 0, 0. By 19 minus 5, I can deduce that 14 answered that. I was like, really? All right, so we have here a better collection of people who agreed. Not here. There's a 2 out of 21 chance of that happening. This one shouldn't be in the group because I asked her yesterday. All right. There's the other person that's not here. What are the odds? There are only 2 people not here. 2 out of the first 3 were in that group, and the other one was asked the question yesterday. Okay, Mahala. Finally got one. There's your indication that, yes, I am randomly grabbing them. So, Mahala, give us some explanation here.
I answered E. It was kind of by deduction, just reading the others and based on the homework that we did. It dealt more with induced EMF and the flux opposed it.
Okay. Well, we had 5 people that said A, so tell me why you didn't choose A.
Because of the word opposed, that's why I chose it. Opposed just seemed like it was more direct and right. Not that I actually memorized the law, I didn't remember it.
Okay. A. Now, somebody else, what is A the answer for?
Faraday's law.
That's Faraday's law of induction. Faraday's law of induction says that a changing magnetic flux induces an EMF. It's a very important law. And in Faraday's law of induction, with the equation form, we put that minus sign to direct us to Lenz's law, which tells us the direction that it will be. And Lenz's law says the direction of the induced magnetic field will oppose the change in magnetic flux. And so you answered correctly, Mahala. It was because you have that opposition. Now, let us have a demonstration. Somebody who has steady hands. Actually, I should just get 2 people with steady hands, and that way I won't screw up, okay? One volunteer is Jordan. I have another volunteer that has steady hands. Right, I could never be a surgeon. I shake. Somebody? Anyone? Okay, Aaron was first. Okay, so what we have here is a copper tube. Copper is not magnetic. Neither of these stick to it. Then I have these 2 things. They stick together. But if I put them here, that one doesn't stick. That one does. So this one here is a magnet. We're going to start with the one that's not a magnet. So one person hold this so it's vertical. So hold the top and let it hang. And then the key is, to be still. And then you drop it through, and I'm going to catch it down here. Well, you can start it halfway in. Okay. When it makes that sound, you know it's hitting the edge. I'm having them do it because I always do that. I usually have a student hold it, and I drop it, and then we have all that. And I'm like, you start halfway in. So you see the difficulty. When I was at PUC, I had like 8-foot pipes that were bigger in diameter and just a magnet with a ball. It was really easy. Okay, that was pretty close. It hit the side a few times, but it fell straight through, right? Now, we're going to do the same thing with the magnet. It stuck a little bit. So don't hold the bottom of it. It won't be any straight. Once you get it halfway in, drop it. Okay, so here we go. Was it rubbing on the side? What was going on here? Yeah, it's cool because it's physics, right? What was going on? Any hypotheses? That's it. Thank you very much, student. Don't worry about it, man. I'll just put them up here. We pay students good money to do that. So what was going on? Any ideas at all?
The magnet also had an induced current in it, so like there was a magnetic field going on that opposed the motion. Or that opposed
Okay, Aaron has pretty much nailed it. Now, the keys here are, of course, this is copper. It's not magnetic. If it was magnetic, what would have happened? It was just stuck, right? No excitement. But the copper is not magnetic, but it is a conductor. So once again, when I was at PUC, when I did this, I had an aluminum tube, a copper tube, and a PVC tube. Aluminum, copper are both conductors. Neither one's magnetic. The two types of things I had rings that I threw here. But the PVC is not a conductor. So what would have happened when I dropped it down, the aluminum versus the copper? Basically the same thing. There is a slight difference because they have a slightly different their resistivity, the amount of energy required to make electrons move, is slightly different for the two materials. So it was a little different. What about when I dropped it through the PVC? Just fell like free fall. So here let's look at the basic explanation that we got from Aaron. So we have a pipe. Here's my pipe. I forgot with this tool, I can't just go ahead and erase like that. I have a magnet that's inside. It's a beautiful magnet. It's like this. Remember, magnets have poles. So I have like a north pole here and a south pole here. What are the magnetic field lines going to do? They come out of north, go into south, and then they go through to make complete loops. So if we look at the region in the tube that's below the magnet, you see the magnetic field lines. As you move away, they spread out, which means the strength of the magnetic field as you move away from the magnet is doing what? Decreasing, which everyone would have known without looking at the lines. I just want to make sure we throw in that. So the magnetic field strength is increasing below the magnet. Since the magnetic field strength is increasing, what does that say? Oh, there it is. What does that say about the magnetic flux in a loop? Well, erase that. In a loop here where I have drawn the bottom, what's happening to the magnetic flux through that loop as it falls? It's increasing. So the magnetic flux is increasing. The magnetic field is pointing down. what does Lenz's law tell us about the direction of the induced current? It's going to oppose the change. So since the magnetic field was downward and getting stronger, Lenz's law says that it's going to make an upward magnetic field. So that means down below, we're going to have current that's flowing in the direction to make an induced magnetic field that's going like that, which means it's behaving like a little bar magnet that has north on the top and south on the bottom. So we have north to north, attractive or repulsive? Repulsive. So if it's repulsive, it's going to provide an upward force. There was a downward force of gravity. The net force is going to be smaller than it would have been if you didn't have the upward force. So it falls more slowly. Now, we had Faraday's law of induction says that the induced EMF is proportional to the rate at which the flux is changing. The faster that magnet falls, the faster the flux is going to be changing, right? And so when it's falling quickly, you're going to have a stronger magnet opposing. When it falls slower, you're going to have a weaker magnet opposing. And so it will fall at the right speed, so the net upward force is equal to the net downward force, right? It'll just find the speed where they balance. Now, that's only half of the equation. We also have the top. What's happening to the strength of the magnetic field as it's dropping at the top of the tube? The magnetic field is decreasing in strength. So that means the flux is decreasing in magnitude. And Lenz's law says I'm going to have an induced magnetic field that's doing what? I know, not supposed to ask it that way. According to Lenz's law, what should the induced magnetic field be doing? That's what you're supposed to ask the question. It should be trying to keep it from changing, so it should be making a magnetic field that's pointing the same direction. So it should be making a magnetic field that's pointing like that, which means it's behaving like a bar magnet. And which pole of the magnet should the magnetic field lines be coming out of? North. So it's behaving like north is down and south is on top. But now we have north to south. Is that attractive or repulsive? Attractive. So we have a current that's above the magnet that's making an induced magnetic field that's attracting it upward. We have a current induced below that's making an induced magnetic field that's repulsive. Both of them are pushing it up. And so it slows it down. This process here of making those current loops we call eddy currents. So the eddy current slowed it down. That experiment tossing the rings was really the same thing. We had a changing magnetic flux in the ring, which created a current loop in the ring, which we call an eddy current, and that current loop was making it so it had a magnetic field opposing that pushed it off. Can you think of a practical application for this? What fundamentally can you do with this phenomenon? It didn't speed it up. It slowed it down. So we could use this to slow something down. And so we can do something like in roller coasters. One of the things that I like is looking at the crazy physics involved that you don't expect in roller coasters. And one of them is, you know, those rides where you go up to the top and then it just drops you down. Anyone been on one of those? It takes you up, you sit up there for like 3 seconds, and then all of a sudden, poof, and you fall, free fall. The ones that are even worse, there's a bungee cord, and so you accelerate downward faster than acceleration of gravity. I don't like that as much. Well, if you look at the tower on those babies, they have like this little vein that sticks out, and then, okay, that's horrible drawing. That's even worse because I erased the wrong line. Undo. erase this line. And then a little ways down near the bottom, it gets bigger. And what you actually have is that's a conducting material, and you have magnets on either side of it. And as it falls, it's going to create eddy currents in that thing that's sticking out that will act as a brake. And as you get down to the bottom, they have a design so the braking is going to get much bigger. That's a good thing, because what if you're on top and they just release you and the power goes out?
Dang.
This here is passive. It's going to brake you no matter what. When I say brake you, I mean slow you down. Not, I will brake you. It's going to slow you down no matter what. So you're going to have a fairly safe landing. And then, of course, you have springs and whatnot. So if the power goes out at an inopportune time, you're not going to die there. So it's a good use. Or let's suppose that you have a volt. Dr. Wolf has a volt. And so it runs on electricity. So you press on the gas pedal, and of course, electricity goes into electric motors. We've talked about how the electric motor works. And then you come to a stoplight and you press on the brake. In a normal car, when you press on the brake, you just have friction. These days, it's almost always on a disc. You just push on each side of a disc with a pad, and the friction between those slows you down. Where does the energy go? Heat, right? So if you watch, like, say you're watching NASCAR racing, or sprint racing. NASCAR is sprint cup. If it's a night race and you look at the wheels, you can see their brakes glowing red because they get hot enough to glow red. Very hot. Well, you would like to have electricity. And so in your volt, you do have normal brakes, but before that activates, you press on the brake, and it's essentially doing this thing. Except for instead of letting the current go somewhere, you have it in a loop, and you use that current that's induced to charge the battery. And so cars like the Volt or a Saturn, when you brake, you're recharging the battery, getting back some of your energy. So cars like the Volt, the Saturn, the Prius, they get really, really good economy for city driving. Normally we get bad economy for city driving because you hit the accelerator, you use energy. You hit the brake, and you dump energy. But with those, you hit the accelerator, energy goes into kinetic energy, you hit the brake, and it goes back to the battery. When you're driving down the freeway, of course, where's the energy going? It's going, if you look at it analytically, it's going into air resistance. You have to put in energy at the same rate, so your power has to equal the power that's being lost to air resistance if you're on a level surface. And so you're not recovering any of that in the car if it's electric car on the freeway. So they get worse performance on the freeway as compared to city driving. Whereas a normal car actually gets better because you're constantly throwing away energy for a normal car in city driving, whereas you're not constantly throwing away driving down the freeway. So it's kind of interesting because everybody is kind of ingrained in them. You get better fuel economy on the freeway than you do in city driving. With electric vehicles, it's reversed because of the technology involved. And of course, as we talked about, when you're driving a car, the air resistance is proportional to speed squared. So in city driving, you're not going as fast. You don't have nearly as much energy lost to the air. All right. Good things, these physics things. So a review of what we've learned about electromagnetism. Electromagnetism is the relationship between electric charge and magnetism, right? Electromagnetism. And what we've seen is that if we have a charge moving in a magnetic field, there's going to be force in the charge. Well, actually, this starts here with the electricity. There are forces between charges. Like charges are going to repel, opposite charges attract. Coulomb's law. Based on that, we have electric fields that we could use to calculate the force. The whole purpose of an electric field is to make it easier for us to calculate forces. Then we went to magnetic charges, and there are also forces between magnetic charges with the same rule. Like magnetic charges repel, opposite magnetic charges attract. So we call the magnetic charges north and south. And you can have stronger north, stronger south. But there's something really different about magnetic charges compared to electric charges. And that is electric charges, you can have just a negative, like an electron is just negative. Just a positive, a proton. But with magnetism, you can't have just the north or just the south. It always comes together, so you always have a net magnetic charge of 0 because you have as much north as you have south. So that's a fundamental difference between the two. We did not ever talk about how strong the force is between two magnets. We talked about how strong the force was for a charge moving in a magnetic field. And then as we learned more, we learned that a charge moving creates a magnetic field. Then we could calculate the force between one current carrying wire and another current carrying wire. But we never did work on the force between two magnets. You can do that, it's just harder. And so we did it. So we finally, in terms of laws, we had Gauss's law that we used to find electric field, Coulomb's law that we used to find electric force. The people in calculus would tell you, we spent a lot of time finding electric fields with Coulomb's law, and we found, with Gauss's law as well. With magnetism, we used Ampere's law in the non-calculus class for finding the magnetic field due to moving charge due to a current. In Physics 252, we also learned about the Biot-Savart law for finding magnetic field from current. And now the last thing we have is changing magnetic flux producing an electric field, Faraday's law of induction. We will, in the next chapter, talk about Maxwell's equations. And James Clerk Maxwell didn't invent any of them. He did modify Ampere's law. It's those three plus the Gauss's law for magnetism. Those are the four Maxwell's equations. He combined just those four equations and determined that you could explain all of electricity and magnetism with just four equations, which is pretty astounding. His first attempt, I think he got down to 21 equations. They had lots of equations people had figured out for different situations, and he was like, well, this and this is equivalent, got down to 21. But then with more study, he got it down to just 4. And so one of the beautiful things in electromagnetism is everything in electromagnetism can be explained by just a total of 4 equations. It's hard, but it all can be explained by those 4 equations. This is a demonstration that I don't have. It's easy to see based on the demonstrations we have seen. If I have a solid metal sheet and it moves through a magnetic field, there's going to be the creation of eddy currents doing loops that will oppose the motion. The same as we saw with the magnet dropping through the tube. But if I have it sliced up, there's very little resistance to swinging through the magnetic field. Why would slicing it up make very little resistance? Yeah, you can't make nice big eddy current loops. You can make little ones like it shows in the picture, but you can't make big ones, so it really restricts the amount of eddy currents you can have and thus the amount of resistance to motion through it. And now the last topic before we get to electromagnetic waves, inductance. Inductance, now Faraday's law, this equation here, that's Faraday's law of induction. It induces or causes a voltage difference by having a change in magnetic flux. So that when we talk about an inductor, we're talking about an induced voltage due to a changing magnetic flux. That's what the word inductor has to do. And this picture here is showing a mutual inductor. Now this mutual inductor has one coil wrapped around a piece of, let's say, iron, and then a second coil wrapped around that same piece of iron. Why do you suppose it's wrapped around the iron? There are two reasons.
It produces a stronger field.
Okay, it produces a stronger magnetic field, and it directs the magnetic field. When you actually have magnets and you store magnets, ideally, you want your magnet, because magnetic fields do a loop, if you have iron material connecting from the North Pole to the South Pole, then the iron material will make it so the magnetic fields can stay within iron, much stronger magnetic field, and do the loop, and you have less stray magnetism. It's going to keep it aligned better. So it'll keep your strength of your magnet better. So this is keeping it so any magnetic field that goes through coil 1 goes through coil 2. So that's the purpose of having that. Now in later pictures, we're going to see a transformer configuration that's taking advantage of this. For my calculations on this slide, I know there's none shown, I'm going to calculate as if it's an air coil. That is if it doesn't have a piece of iron in there. The reason is, if you have that piece of iron in there, it complicates the math just a little. And I don't want to complicate the math. So we're going to pretend that it's just air, but that you're going to have exactly the same magnetic field going through one as you have going through the other. Everybody understand my approximations here? Okay. So let's look at this. Let's suppose that I have a current going through coil 1. If I have a current going through coil 1, that should create what inside of the coil? A magnetic field. And we have an equation for that says the magnetic field due to coil 1 is equal to mu naught multiplied by the number of turns in coil 1 divided by the length of coil 1 multiplied by the current through coil 1. Right, that was our equation for the magnetic field inside of a solenoid. But if I have that magnetic field going through coil 2, it can induce a voltage. And what's the equation? You can just give me the name rather than blurting out all of the pieces. What's the equation that tells me about the voltage induced in that second coil? Somebody said it correctly. Faraday's law. Thank you, Mahala. So Faraday's law says that the voltage in coil 2 is equal to minus N2 change in magnetic flux over change in time. Minus N2, the magnetic flux is going to be the area. The area is a constant, so I'm just putting it as A because I drew them as the same area. The picture shows the same area. And then mu naught N1 over L1, change in current 1 over change in time. Why change in current 1? Because it was the change in flux. We're not changing the area. We're not changing the number of loops. We are just having the current that can change. So simplifying that, E2 is equal to minus N1, N2. Actually, we usually put the mu out front, so let me put the mu out front. So we have, that's the relationship between the voltage that's induced in the second coil and the current that's going through the first. Now here's something really, really important. If I have a constant current, how much voltage am I going to induce in that second coil? 0. Because I have to have a change in magnetic flux to induce voltage. And to have a change in magnetic flux, I'm going to have a change in the current going through the first one. Now this here, for an air coil, this here we call the mutual inductance M. It gets a little more complicated in reality, but that's what we're going to call the mutual inductance. I actually spent a lot of time trying to figure out why, when I looked at other equations for mutual inductance, it had a mu sub R in there. And that mu sub R was because of having the iron core in there, and it depends on the material as well as the geometry. So what we have is a voltage induced in the second coil due to a current in the first. This mutual inductance. The mutual means it's between two different coils, is the key to a transformer. Now, these days, you have a whole series of really crummy movies that apparently a lot of people watch, the Transformers, that are, more than meets the eye. Purportedly robots in disguise. Well, when we talk about transformer in our physics class, we're going to be talking about a device like this. Here we have an iron core. That iron core is not a rod, it's shaped in a loop. Based on what I've said, why would you want it shaped in a loop? It's going to direct the magnetic field. You're going to have very, very, very weak magnetic fields outside of that coil, or that iron core, and very strong magnetic fields inside. So as a percentage of the area you put in, words are escaping me left and right here. As a percentage of the energy you put in, a very, very tiny fraction is going outside of the iron. Hence, you're not going to lose very much. Now, there is a downside. If I put a magnetic field on the iron, it causes those little domains inside to rotate. That's why it has its large permeability. But if I'm going to make something physically rotate, well, that took some energy, right? So there's work involved with making it rotate. So you do have some loss there. But a transformer like this can have an efficiency that's better than 95%, right? You lose less than 5% of your energy in the transformer because of the design. And so actually, when they design these for, you have power transformers and signal transformers, different designs for loss. But what's important about this is, and these are the full-on equations for the relationship between the voltage in the primary. The current going through the primary has two pieces, one the resistance and one inductance, and then you have the mutual inductance and the current in the secondary. The equations are symmetric so that it turns out that that's, okay, can't circle important pieces. This is your important equation to describe an ideal transformer. The ideal transformer allows you to vary the number of loops in the primary side, the side you're putting power to, and the number of loops in the secondary side, the side you're taking power off of. And by so doing, the ratio of those numbers of loops gives you a ratio in the voltage output. So if I have something here in the United States that runs off of 120 volts AC, and I go to Malaysia and I have something that runs off of 240 volts AC, and of course you might see 110 and 220. Our voltages vary throughout the day. When there's high demand, they actually lower the voltage that comes out of the plugs, because that's lowering the power that you're going to use so that they can supply electricity to more people, and you don't notice really the difference. Most people don't realize that. So the actual voltage coming out depends on where you are and when you measure it. So we're somewhere between 110 and 120. And in Malaysia, somewhere between 220 and 240. So if I have something that's designed to run on, let's say, 110 volts, and I go to Malaysia and coming out of the socket is 220 volts, if I have a two-prong, I can actually jam that two-prong thing in there. What's it going to do? Fry it, right? That's bad. So what I need to do is to cut the voltage in half. Well, the transformer is perfectly designed for that. With the transformer, I need my V2 to be 1/2 of V1, right? I need V2 to be 110 when V1 is 220. So I just say V2 is equal to 110 volts because that's what I need for my device. V1 is equal to 220 volts because that's what's coming out of the wall. And so using that equation, V1 over V2 is equal to N1 over N2. Then I get the fact that I'm going to have N1 over N2 is equal to 2 over 1. So however many turns I have in, well, let's just solve this for N2, or N, yeah. So I'm going to have N2 is equal to N1 over 2. So however many terms I have in the primary, if I have half that number in the secondary, then I'll have the proper step down. Now, you usually don't do 2 to 1. You usually do something like, 2,000 to 1,000. But that's how the transformer works. And if it's an ideal transformer, you don't have any power loss. So since power is IV, that's where the other half of the equation comes in. If I1 V1 equals I2 V2, and V1 over V2 is N1 over N2, then that gives you the second half of the equation that N1 over N2 is equal to I2 over I1. So it's also going to change the current. If you step the voltage down, what does that do to the current? It steps it up. So I have a device that needs 110 volts and is going to use 0.2 amps. I make my 2 to 1 ratio, so I have 220 volts, and what was the current coming from the wall? If I'm using 0.2 amps on the output side, what's the current that's coming from the wall? 0.1, right? So it was less current, more voltage out of the wall, more current, less voltage going to my device. So that's how a transformer works. You can see that it has some real practicalities. And of course, with our electric distribution system, we use these. Now, I have questions on electric distribution system, but I should ask the next question first. It's actually 2 questions. What is the output voltage of a transformer with N1 equals 100, N2 equals 200, V1 equals 12 volts DC? Batting 50%. Oh. Okay, waiting for Megan and Caitlin. Just Caitlin now. Wouldn't it be nice if it stayed logged in? What are the odds I grab James again?
Well, it's logged in, it's just frozen.
Oh, it's frozen. Perfect. Okay, there it answered. Okay, we started off with a 50-50 mix. We ended up far from it. Let's go to Jordan. How many people know that in Japanese that means joke? I was in Japan during the 92 Olympics, and Michael Jordan was the star of the team, and everybody thought it was so funny because Jodan is joke, and that's how they pronounce Jordan. Okay, so Jordan.
Well, if you have V2 over V1 equaling N2 over N1, N2 over N1 would equal 2 to 1, so therefore it'd be 12 times 2, which would be 24, and that's my answer to A.
Okay, he answered A. We had 3 people that answered B. They were 3 of the first 5 people to answer. Somebody want to explain why they answered B? Go ahead.
Can't you not use a transformer with direct current? Don't you have to have alternating current?
I asked this because I put this on the test before and people got it wrong because they didn't pay attention. It has to be AC, alternating current, because you have to have a changing flux. Alternating current will steady it more very soon, like Monday, I think. But you have the current going up and down for the alternating current. That's what you need. So we have the follow-up question. What if we change it to AC? Okay, this time, oh no. 18 agreed with Jordan. Now that we've changed it to AC, one person stuck with this. If it's AC, then the transformer works. Okay, now I mixed them up. Have a great weekend. I'll see you on Monday.
Would the output voltage still have to be AC though?
Yes.
Okay.
Oh, I didn't see that. Yeah, I copied. I had gone through this before, but there was a little mark on one. I didn't want to go through and reformat everything, so I just changed the one AC. You're right. Should have had ACs on all these. Good call.